Good morning, students. Welcome to Bindu Dhadwal Chemistry Lessons. Our topic for today is physical properties of aldehydes and ketones, and we'll take up structure of carbonyl group and some chemical properties of aldehydes and ketones also. So, first physical property is physical state. So, formaldehyde or methanol is a pungent smelling gas. Ethanol is a volatile liquid, but aldehydes and ketones up to 11 carbon atoms are colorless liquids, and other higher members having carbon atoms more than 11 are solids at room temperature. Smell. With the exception of lower aldehydes, which have unpleasant odors, aldehydes and ketones generally have pleasant smell. As the molecular mass increases, the odor becomes more fragrant. So many naturally occurring aldehydes and ketones are also used for blending perfumes and as flavoring agents. Solubility of aldehydes and ketones. Up to 4 carbon atoms, the aldehydes and ketones are miscible in water. This is because they can form hydrogen bonding with hydrogen of water molecules. The polar bond, carbonyl bond, is polar. The negatively charged oxygen of a carbonyl group will be engaged in hydrogen bonding with the positively charged hydrogen of water molecule, and so it's soluble in nature. But the solubility decreases with the increase in number of carbon atoms. This is because as the group increases, the bigger groups mask the smaller carbonyl group, and so hydrogen bonding becomes difficult. Aldehydes and ketones are soluble in organic solvents such as benzene, ether, chloroform, alcohols, etc. Ketones themselves are good solvents. Boiling points. Boiling points of aldehydes and ketones are greater than the non-polar compounds like hydrocarbons, or weakly polar compounds like ethers, but they are less than more polar alcohols and carboxylic acids. This is because aldehydes are polar compounds, carbonyl group is polar, then there are dipole-dipole interactions within themselves, so greater heat is required to break the force of attraction, dipole-dipole interactions between adjacent molecules. So boiling point is higher than non-polar or weakly polar compounds. But the boiling point is less than that of alcohols and carboxylic acids because dipole-dipole interactions are weaker than the intermolecular hydrogen bonding which exists in alcohols and carboxylic acids. So let's compare of comparable molecular masses. Butane, a non-polar compound, has boiling point 273 Kelvin, whereas the ketone and the aldehyde with molecular mass 58 has greater boiling point 322 Kelvin. Ketone has 329. Ethers have less, 281. Alcohols have greater than aldehydes and ketones, 370. Among carbonyl compounds, ketones have greater than boiling point than isomeric aldehydes and ketones. This is because there are more electron releasing alkyl groups in ketones than in aldehydes, and these electron releasing groups make the carbonyl bond more polar. So boiling point of ketones will be greater than that of aldehydes. For example, the propanol has dipole moment 2.52 dBi, whereas propanone has 2.88. Its dipole moment is greater. So greater dipole moment means greater interaction, greater boiling point. Chemical properties of aldehydes and ketones. So the chemical properties are due to the polar carbonyl group. So let's do the structure of carbonyl group to understand the properties. So in the carbonyl group, the carbon atom of the carbonyl group is sp2 hybridized. So it forms 3 sp2 hybrid orbitals. These 3 sp2 hybrid orbitals will form sigma bonds, one with oxygen atom and 2 with either hydrogen or carbon of alkyl groups. And the unhybridized p orbital will overlap sidewise to form a pi bond with the unhybridized p orbital of oxygen atom. So this sp2 hybrid bonds are planar in nature, whereas the pi bond is perpendicular above and below. The pi bond electrons are present above and below the planar sp2 hybrid structure. The bond angle of the compound is 120 degrees. This carbon oxygen bond angle is 120 degrees. So this carbon, because oxygen is more electronegative than carbon, so this bond is polar with a partial negative charge on oxygen atom and partial positive charge on the carbon atom, because electrons are attracted towards the more electronegative oxygen atom. So because of this polar nature, the carbonyl carbon is an electrophile, means it's seeking electrons. It's electron deficient in nature, so it will act as a Lewis acid. And the carbonyl oxygen, because it's partially negatively charged, behaves like a nucleophilic atom, behaves like a Lewis base. Polar nature of carbonyl group is supported by the fact that aldehydes and ketones have large dipole moment. We can see that they have large dipole moments, which also indicates that they are polar in nature. So the dipole moment varies between 2.3 to 2.8 dBi. For example, ethanol has a dipole moment of 2.72 dBi and propanone or acetone has a dipole moment of 2.88 dBi. The high polarity of carbonyl group is explained on the basis of resonance between the neutral and dipolar structures. So in the neutral structure, we have a double bond between carbon and oxygen, and due to resonance and due to the electronegative nature of oxygen atom, the electrons of the pi bond are attracted towards the oxygen bond, resulting in a negative charge on the oxygen atom and a positive charge on the carbon atom. Differences between the carbon-carbon double bond and carbon-oxygen double bond. So this ethylenic double bond and these carbonylic double bond, they have some differences. So one is that molecules like halogen, hydrohalic acid, sulfuric acid, they undergo addition reactions in case of ethylenic double bond, whereas addition does not occur in carbonyl group. Another is that the addition reaction that occurs is electrophilic addition reaction in case of carbon-carbon double bond. It is nucleophilic addition reaction in case of carbonyl group. The reason behind this is that carbon double bond carbon is non-polar, whereas carbon double bond oxygen bond is polar. There is no resonance in this non-polar bond. There is resonance in this polar bond. Reactions of aldehydes and ketones can be categorized into 5 categories. Nucleophilic addition reactions followed by elimination of water molecules, oxidation reactions, reduction reactions, and miscellaneous reactions. So let us begin with the first category, nucleophilic addition reactions. So as you know that the carbon-oxygen double bond or the carbonyl group is polar in nature, it is highly reactive, and this is because of higher electronegativity of oxygen. The electrons are attracted towards oxygen, resulting in establishment of negative charge on oxygen and partial positive charge on carbon atom. This positively charged carbon atom will attract a nucleophile towards itself. The attack occurs, this portion is planar attack occurs perpendicular to the planar nature of the carbonyl group, and attack will occur from the top face. Nucleophile will attack when the electrons are shifted from the electrons of the pi bond are shifted from the pi bond to the more electronegative oxygen atom. A nucleophile will go to the electron deficient carbon atom from the top. As a result, the electrons migrate towards the oxygen atom. Because electrons migrate, nucleophile gets attached over here and an intermediate is formed. Now here it was sp2 hybridized, but when it forms 4 bonds, it's an intermediate of tetrahedral shape, and sp3 hybridized, and the shape changes from planar to tetrahedral, nucleophile being on the top, and 3 groups are present at an angle of 109 degrees 28 minutes. In the next step, after the formation of intermediate, a proton gets attached, and this reaction is fast and an addition product is formed. The step where nucleophile is attached is slow and is the rate determining step. So step 1 is slow, step 2 is fast. Net result is that there is addition of a nucleophile to carbon and of a proton to oxygen of the carbon-oxygen double bond. If the attacking nucleophiles are weak, for example, ammonia and its derivatives, then the reaction of aldehydes and ketones are usually carried out in weakly acidic medium, and such reactions are called acid catalyzed nucleophilic addition reactions. So in acid catalyzed addition reactions, initially a proton will be added to the electronegative oxygen atom when electrons migrate towards it. So these electrons migrate and proton is added. Then, because the carbon atom becomes electron deficient, then the nucleophile attacks on this carbon atom to form the addition product. Relative reactivity of aldehydes and ketones. Aldehydes and ketones undergo nucleophilic addition reactions readily, but ketones are less reactive than aldehydes. This is due to the electronic and steric effects. So let's do them one by one. Electronic effect or inductive effect. So the relative reactivity of aldehydes and ketones in nucleophilic addition reaction may be attributed to the amount of positive charge on the carbon atom. A greater positive charge means a higher reactivity. Now, if the positive charge is dispersed throughout the molecule, then the carbonyl compound becomes stable and its reactivity decreases. This dispersal occurs when there is an electron releasing alkyl group. So we see that in formaldehyde there is no electron releasing group, so the positive charge stays on the carbon atom and it's very reactive. When an electron releasing group is added, for example in aldehydes, the positive charge is dispersed, the positive charge becomes less, reactivity will decrease. When more than one group is attached, reactivity is still further decreased because positive charge is still further dispersed. Second effect is steric effect. The size of alkyl group is more than that of hydrogen, so it causes hindrance to the approach of nucleophile. So larger alkyl group causes hindrance to the attacking group. This is called steric hindrance. As the number and size of alkyl group increases, the hindrance to the attack of nucleophile also increases and reactivity decreases. So these formaldehyde will be most reactive because it contains smaller hydrogen atoms and nucleophile can approach easily. In case of aldehydes, the alkyl group is bulkier than hydrogen atom, so there is a little steric hindrance caused to the approach of nucleophile. In case of ketone, there are two such bulky alkyl groups, so the hindrance is still further increased and reactivity decreases. When the group becomes bulkier, for example, this is a secondary alkyl group attached, so hindrance is increased, reactivity is further decreased, and the least reactive will be di-tertiary butyl ketone because it's offering maximum steric hindrance. So as we move to bulkier alkyl groups attached to the carbonyl group, the steric hindrance increases and the reactivity decreases. So this is the reactivity order. Formaldehyde is most reactive of all. In case of aromatic aldehydes and ketones, the aromatic aldehydes and ketones are less reactive than aliphatic aldehydes and ketones. For example, benzaldehyde is less reactive than aliphatic aldehyde. This can be understood from the resonating structures of benzaldehyde. We see that when the electrons move to the oxygen atom, the electrons of the phenyl ring will move towards it, decreasing the positive charge on the carbon atom and thus decreasing its reactivity. So, of the 5 resonating structures that you draw, first is a carbonyl group and phenyl group with 3 double bonds. The second structure will be where the double bonds have moved to alternate positions, and in the next structure we can construct by shifting these electrons to the more electronegative oxygen atom, because of which there's a positive charge here, so electron of the next double bond will move here. As a result, there's a negative charge in the next structure on oxygen atom. Double bond changes to single bond changes to double bond, and because electrons have moved here, there's a positive charge here. So this is the next structure. There, the 2 double bonds are present here. Because of the positive charge here, we can arrive at the next resonating structure. So electrons will move to this end and a positive charge will come over here. In the next structure, these double bond electrons move here and a positive charge will come here. The rest of the structure remains the same. So these are the 5 resonating structures, and due to resonance we see that the positive charge on carbon atom decreases because of shift of electrons of the benzene ring towards it. So the reactivity decreases. But amongst aromatic aldehydes and ketones, aromatic aldehydes will be more reactive than ketone. So benzaldehyde will be more reactive than methyl ketone and methyl phenyl ketone, and which will be more reactive than benzo ketones, diphenyl ketones. And that's all in today's video. If you like the video, please do share and subscribe.